Section 3.1 and 3.2 is going to be our first lesson, and that's going to be over functions. Okay, before we can define what a function is, we first need to define a relation. A relation is something that relates one set of things, call that the domain, to another set of things. We'll call that the range. Okay? A function is a special type of relation. A function is a relation where every element of the domain corresponds to only one element of the range. Okay? So, let's talk about different possibilities of what could be a function or not be a function. So let's say we have a group of students. Let's say we have students A, B, C, and D. And let's say that all four of them had heights of 5 foot 2 inches, 6 foot 1 inch, 5 foot 7 inches, and say 5 foot 10 inches. Let's say student A is 6 foot 1, student B is 5'7", student C is 5'2", student D is 5'10". This shows that every element of the domain corresponds to only one element of the range. This is an example of a function. And this will be true for everybody's height because every person in the world only has one height. Okay, so it only corresponds to one thing. Let me give you another example. My siblings is Amanda, Evan, Austin, and then myself, Andrew. We're going to be the domain. And let's say we have some dates over here. Say March 21st, August 27th, and January 14th. And the relation between the people in the domain and the dates in the range is going to be birthdays. That's my sister's birthday. That's my brother's birthday. And me and Austin share the same birthday because we're twins. Now, is this a function? Well, the definition of a function says everything in the domain corresponds to only one thing in the range. Well, in this case, it is still a function. Even though Andrew and Austin go to the same thing, they're only going to one thing. So this is a function. Okay? Let's do an example of something that's not a function. Let's say we have students A, B, C, and D. And let's have that be the domain, and let's have the range be the different types of cars they own. Let's say student A owns a Ford. Let's say student B owns a Chevy. Student C owns a Pontiac. Student D owns a Toyota, but he also has a Dodge. Okay, because he owns two cars. Well, in this case, we have something in the domain going to two different things in the range, which contradicts what the definition of a function says. So, this is not a function. Okay? So, when we extend that to algebra, we say the domain is going to be the x values. And the range is what we put into a function, and we get out something, is going to be the y values. We get out a y value. Okay, so let's do some ordered pairs and see if they're functions or not. So here's a set of ordered pairs. Now, is this a function? Well, what we need to look for is see if any of the x values go to more than one y value. You see that we do not have a repeat of any of the x values. They all go to different things. So this is a function. Here's another example. Got a set of ordered pairs. We're looking to see if any x value goes to more than one y value. Now you see right here we have 3 and 7 both going to 5. But what we're really worried about is to make sure there's no repeated x values. We don't necessarily care about y values. That was like Andrew and Austin both going to January the 14th. So this one is a function. Another example here. Is this a function? Again, we're looking to see if we have any repeated x values. And right here you see we have 3 going to 8 and a 7. That would make it not a function because we have the same x value going to two different y values. Okay. Now, how can we tell on the graph? Okay, the graph of we can tell something by the graph. If a function is a graph, we can tell by if something is a graph of a function by seeing if it passes the vertical line test. The vertical line test says if a vertical line intersects a graph at more than one place anywhere on the graph, then that function, that graph is not a function. Okay? So let's look at some examples. Oops. Say I have a graph. Okay? If you look at this graph, there is nowhere on this graph where a vertical line, a perfectly vertical line, will intersect that graph at more than one place. It's always going to intersect it at one place. Okay, so this guy is a function. Okay? Look at this guy. This is an example of a graph that's not a function, because anywhere along here I can draw a line that'll intersect it at more than one place. This one's not a function. And that's really all there is to it. Just look at it and say, is it a function or not a function? Look at this one. Function or not? It is a function. What about this graph? Is it a function or not? It's not a function. There's an example of a vertical line intersecting more than one place. Here's another example. Function or not? It's not. It intersects the graph at more than one place. Okay, so that's how we determine by looking at a graph. Now, let's talk about something called function notation. Okay, function notation basically uses the simple fact that y equals f of x. So if I have something like this, function notation says we would write f of x equals 2x squared minus 5x. We read this as f of x. That is short for function of x. Okay, so why is this handy? Why do we use function notation? Well, basically it's set up to where whatever's in the parentheses we will plug straight into the function. So if it says, if it says I want to find f of 1, that means I do, if it's 2x squared minus 5x, I would do 2 of 1 squared minus 5 times 1, which is 2 times 1 minus 5, or 2 minus 5, which is negative 3. What about if I want to find, say, f of negative 3? That's 2 times negative 3 squared minus 5 times negative 3, which is going to be 2 times 9 minus, or say plus 15. 18 plus 15 is going to be 33. What about if I do, say, f of h? That's going to be 2 times h squared minus 5 times h, which simplifies just 2h squared minus 5h. What about f of n plus 1? That's 2 n plus 1 squared minus 5 times n plus 1. Multiplying that guy out, that's going to be n squared plus 2n plus 1 minus 5n minus 5. 2n squared plus 4n plus 2 minus 5n minus 5. Simplifying, 2n squared minus n minus 3. Okay? So let's talk a little bit about domain and range. I've already said that the domain is what we put in, it's the x values, and the range is what we get out, or the y values. Let's talk about specifically about the domain. What can we put in? What can we put in? Well, we're really not limited by anything except a couple different things. Things we cannot do algebraically in algebra. We cannot divide by 0. And we cannot take a square root of a negative number. So those are things that will limit our domain. So let's define the domain of some functions. Let's say I have f of x equals x squared plus 5x. Now if I look up here, there's two things I can't do. I cannot divide by 0, or I can't take a square root of a negative number. I do not have a division or a square root on this problem. So there's nothing that's going to limit my domain. So I can plug in all real numbers. That's everything I can plug in there, which in interval notation is from negative infinity to infinity. Set notation is that symbol which represents all real numbers, or you can say x such that x is an element of the real numbers. Okay, this is interval notation. And this is set notation. Okay? So if there's no limits, then it's just going to be all real numbers. Now, what if there is some things that would limit that? For instance, let's say g of x is 3x over x squared minus 4. Okay? Well, we have a division. We know that this part cannot equal 0. The bottom part not equal 0. So I say that x squared minus 4 cannot equal 0, which tells me x cannot equal plus or minus 2. So it would be all real numbers. Oops. Except when x equals positive or negative 2. So in interval notation, from negative infinity up to negative 2, from negative 2 to 2, and from 2 to infinity. That's interval notation. Set notation, okay, it's x such that x is an element of the real numbers and x does not equal 2 or x does not equal negative 2. Okay? Here's another example. Say the square root of 4 minus 3x. Okay, we know we can't take a square root of a negative, so this guy always has to be greater than or equal to 0. Subtract 4 from both sides, divide by negative 3. When I divide by a negative, the sign changes. So x is always going to be less than or equal to 4/3. Okay? Always going to be less than or equal to 4/3. So it's all real numbers except it has to be less than or equal to negative 4. So it'll be from negative infinity up to 4/3 with a bracket. That's interval notation. Set notation. It's basically just x is a real number such that x is less than or equal to 4/3. Okay, that's the two different possibilities, and there can be a combination of both. Let's say h of x is some square root of, no, I don't want the squared on there. Square root of 3x plus 12 all over x minus 5. Well, first off, we know x minus 5 cannot equal 0, so x cannot equal 5. We also know that 3x plus 12 has to be greater than or equal to 0. So 3x is greater than or equal to negative 12, or x is greater than or equal to negative 4. So in interval notation, the lowest it can be is negative 4, and the only place it messes up is at 5. So I have a little jump at 5, and it goes on to infinity. Okay. In set notation, it's x such that x is greater than or equal to negative 4 and x does not equal 5. Okay. Now, that's how we define domains of functions. Let's talk about different operations we can do with functions. We have our 4 operations: adding, subtracting, multiplying, and dividing. So let's see how they carry over with functions. They all carry over pretty well. Say you have f plus g of x. That notation is saying add the 2 functions, and it is simply just add those 2 functions. Say you have f minus g of x. That's going to be f of x minus g of x. Let's not do divided by yet. Let's do multiply. F times g of x. That's just f of x times g of x. F divided by g of x. F of x divided by g of x. So let's say I have an f of x is equal to x squared plus 2x, and I have a g of x equal to x squared plus 5x plus 6. Let's perform these different operations. Let's do f plus g of x. That is f of x plus g of x. Okay, that's going to be x squared plus 2x plus x squared plus 5x plus 6. If I drop my parentheses, nothing really changes. Combine like terms. I have 2x squareds, 7x's, and 6. Let's say I do f minus g of x. That's f of x minus g of x. That's going to be x squared plus 2x minus x squared plus 5x plus 6. Now, I got to distribute the negative sign to all the terms on the second parentheses, so it becomes negative x squared, negative 5x, negative 6. Then combine like terms. My x squareds go away. I have 2x minus 5x, which is negative 3x, and then the negative 6. Okay, let's do f times g of x. That's f of x times g of x. It's going to be x squared plus 2x times x squared plus 5x plus 6. Using the distributive property, I get x to the 4th plus 5x to the 3rd plus 6x squared plus 2x to the 3rd plus 10x squared plus 12x. Combine like terms. I only have one x to the 4th term. 5x cubed plus 2x cubed is 7x cubed. 6x squared plus 10x squared is 16x squared. And then I only have one x term, 12x. And the last is f divided by g of x. That's f of x divided by g of x. That's going to be x squared plus 2x divided by x squared plus 5x plus 6. You see the top part, I can factor out an x. And I get that. The bottom part factors into x plus 3, x plus 2. You can see that the x plus 2's cancel. And I'm left with x over x plus 3. Okay, that's the 4 operations, basic operations, and they transfer to functions just well. So that'll end this lesson.